Yeah, thanks a lot for the invitation. And yeah, so this is joint work with Reid Barton from CMU. And so the plan for today is that I want to give a little bit of motivation for why I got interested in this idea of condensed type theory, and then talk about the axioms of condensed type theory, and very briefly about some models, then some weird feature that we stumbled upon that we call directed univalence. Then I briefly want to talk about the real numbers in condensed type theory and some future ideas. So a first motivation is maybe you could wonder about a computer algebra system for general topology. And so obviously there's a lot of numerical modeling software to compute with real numbers or floating point numbers. And yeah, so you can do a bunch of real topology and analysis with those systems. And from one point of view, you could think of homotopy type theory or some cubical variants or whatever as a sort of computer algebra system for homotopy theory, where you work with spaces up to homotopy. And so we absolutely do not claim that what we have is a computer algebra system for general topology, but you could see it as like one little step towards something like that, where you can just say, let X be a space, and then hopefully do computations with it. So a different motivation is directed type theory. Okay, this is a motivation for the talk, not a motivation why I was interested in this project, because we only stumbled upon this after we got interested. But anyway, so what is the idea of directed type theory? Well, so if you're doing category theory and you want to specify a functor, then you just say what the functor does on objects. And then every soul can infer the action of the functor on morphisms. But computers don't have a soul. So directed type theory wants to make something in which every object that you work with is some sort of category, and every function is automatically functorial with the correct variance. So somehow the system will be able, sort of from the syntax, to infer how everything is functorial. And so condensed type theory provides some results of this flavor, and we'll get to that later on in the talk. And so another motivation for me to be interested in this was this liquid tensor experiment that we ran in the Lean community a couple of years ago. And so this is all about some sort of liquid analytic ring structure on the real numbers, whatever that may be. And so the whole problem, the reason why Schulze, or one of the reasons why Schulze challenged us to work on a formalization of this proof, was that the proof is pretty complicated, and according to Schulze, it doesn't really fit in a human brain. And I haven't really heard of anyone who challenges that claim. And so we verified this proof in the liquid tensor experiment. And then Reid Barton came to Freiburg. I was in Freiburg back then. And we spent a bunch of time thinking about how we can sort of try to reorganize elements of the proof in such a way that it would actually fit in a human brain. And so condensed type theory was one of the sort of side effects of thinking about this. And we hope that somehow it might be able to be used as one ingredient of reorganizing the proof, but it's not completely clear yet. And certainly what I'm presenting you today will not be the final answer. Okay. Then, sort of hot off the presses, 2 weeks ago, we discovered that there is a different group of people in Sweden, in the group of Thierry Coquin. And so Felix Cherubini and Freek Geerlings are involved. And they also have a version of condensed type theory. They start with Boolean algebras and then have a bunch of axioms. We do not talk about Boolean algebras. You'll see our setup in a minute. So it turns out that there is quite some overlap, but our motivations and applications are really quite different. So that's sort of an interesting coincidence. Right, and so, okay, that was a bunch of motivation, background, etc. So let's get going. So in this seminar, I don't really have to explain what type theory is. You all know that there is this sort of Rosetta Stone. You can think of type theory and sort of intuitively model this or have semantics where you think about it like sets and functions and products of sets and that kind of stuff. And then there is the logic interpretation where you think of types as propositions and terms or proofs, etc. Homotopy type theory would put an extra column next to this where you think of types as homotopy spaces or spaces up to homotopy. And we sort of want to add an extra column to this Rosetta Stone where it's not spaces up to homotopy, but honest spaces. And elements will be honest elements and not just elements up to paths or anything. And so the starting point will be dependent type theory in the sense of Martin Löw. And then on top of that, we'll be adding some axioms. So what does that look like? We first of all start by postulating two predicates on types. And so the two predicates are, first of all, CHaus. So a type can satisfy this predicate CHaus, or ODisc. And ODisc, the O stands for overt, and disc stands for discrete. So overt, discrete. In the end, we typically just call them discrete, even though this is maybe slightly imprecise. And then CHaus, of course, stands for compact Hausdorff. And we will abuse notation, and instead of treating these as predicates on types, we treat them as sort of sub-universes. And this means that we'll talk about types whose type is CHaus and types whose type is ODisc. Right, so very informally, we'll be thinking of every type as a topological space. A bit more precisely, you could be thinking of it as a condensed set. And then saying that a type A is CHaus means that we think of A as a compact Hausdorff space. And when we think of A, when A is a type that is ODisc, then we think of A as a discrete space. And somehow this O, you can't really see this O in this naive interpretation, this overtness. You can already see it a bit better when we add a context. So if we have a type within some environment, some context gamma, so our type maybe depends on certain other types and terms, etc. Then the way you model this is as a map. So then A would be a topological space or a condensed set, and the map to, so the context would also be modeled by some sort of space, and the fact that A exists in this context would mean that you have some sort of maybe a vibration kind of thing. And so in this case, it would be a proper map if A is CHaus, and a local homeomorphism in the case of ODisc. So we're not just asking for discrete fibers, for example, in the ODisc case, but we really want the discreteness to also vary continuously, which means that you want a local homeo. And that is sort of also this overtness is capturing that aspect, that you don't just have discrete fibers. Okay. So now, of course, we need to know, like, it's nice that we have these two predicates and we give them fancy names, but we can't do much with that. So now we will be looking at a bunch of axioms that explain how these two predicates, how these two subuniverses interact. And they should be interacting in such a way that they that justifies that we call them CHaus and ODisc. So first of all, we have a bunch of sort of basic axioms. And so we want, if you take a finite product of types that are CHaus, then the resulting product should also be CHaus. And the same is true for finite disjoint unions. If you take a type that is CHaus and you have an equivalence relation that is like a closed equivalence relation. So the equivalence relation, that will be some prop. The prop is a type, that proposition is a type, and hence it can be CHaus. So if it's a CHaus proposition, this equivalence relation, then you can form the quotient, and the resulting quotient will also be in CHaus. Of course, if two types are isomorphic and one of them is CHaus, then so the other should be as well. And so the subuniverses should also be closed under formation of sigma types. So if your indexing type is CHaus and you have a family of CHaus types, then you can form the sigma type, and that should again be CHaus. And the same should be true for ODisc, all these axioms as well. Okay, so that's sort of basic and standard, and it matches our intuition that a product of two CHaus spaces is again compact Hausdorff, and the same is true for discrete. And then we postulate two mild versions of the axiom of choice. So the picture is as follows. We have a commutative triangle like this, and so it starts with the map F on the right. So we have a compact Hausdorff space Y, and over that lives a random type X. We don't assume that X satisfies one of the special predicates. And so we have the map F from X to Y. And then what we want is that there exists another compact Hausdorff type Y prime that is covering Y. So there should be the horizontal map in the picture should be a surjective function from Y prime to Y. And we want a section. So we don't want a section of F directly, but we sort of want it that it exists locally, sort of, and G specifies how we think of it as a local section. So there should be a map from Y prime to X that splits F up to this cover G. And so we have this axiom of choice for CHaus, but if you replace CHaus in both places with ODisc, then that is our collection axiom for ODisc. So we don't call it an axiom of choice, we call it collection for historical reasons. These axioms first showed up in, I think, a paper by Johan and Moerdijk, and they call it collection axioms. And so we copied that. Okay. And so now we start getting into the more interesting territory, where we start seeing the sort of topological flavor of our axioms. So recall that we already claimed that the two subuniverses should be closed under sigma types, which is one of the important ways to create new types in independent type theory. And the other one is pi types. And so sort of we want, if you start with types that live in the subuniverses CHaus and ODisc, then you want to know what happens if you start combining them with the classical type formers like sigma types and pi types. And so we had the sigma axioms, and now we'll have the pi axioms. And so if you have a discrete indexing set, and a family of compact Hausdorff spaces indexed by this discrete set, then we want that the product of those compact Hausdorff spaces is again compact Hausdorff. And that's exactly Tichonov's theorem. So not only a finite product of compact Hausdorff spaces is again compact Hausdorff, but also infinite products. And in classical topology, whenever you take an infinite product, it will always be indexed by an ordinary set. And that indexing set doesn't really carry any sort of topological structure. And that's sort of captured by the fact that our indexing set has to be discrete in this axiom. But then dually, if you have a compact Hausdorff indexing set and a family of ODisc spaces indexed by I, and now you form the product, then we want this to be we want this product to be an ODisc space. And so this is maybe slightly less intuitive coming from topology. But for example, if we take for x a constant family, so then we're just looking at a function type. We're looking at functions from I to, let's say, x. And so now this is saying something about the compact open topology on the space of continuous maps from a compact space to a discrete space. So in that sense, it sort of extends that bit of intuition. Okay. Yeah, there are a few more axioms to come, and they're all, yeah, I would say they're more interesting than the basic ones. So Tichonov was already not very basic. So now we have something about factorization. This again will match topological intuition. So we start with a compact Hausdorff x and an ODisc y. And now we look at a function from x to y. So we have a function f, and we postulate that any function from x to y will factor through fin n, where fin n is like the canonical finite type with n elements. So typically the subtype of the natural numbers consisting of numbers 0 up to n minus 1. And so what this is saying informally is that every map from a compact Hausdorff space to a discrete space has finite image. And so the sort of topological slogan is that compact in discrete is finite. Okay. And then finally, there is a sort of somewhat mysterious axiom that in things like synthetic topology is called Scott continuity. And so it works as follows. We start with an indexing set and a codomain that are both ODisc, and a family of compact Hausdorff spaces indexed by I. And now we look at functions from this product of xi's that are indexed by I, and we look at functions to y. Okay, so what do we know from previous axioms? We know that this product of xi's is going to be CHaus, and we already know that y is ODisc, so this map is going to factor through a finite set by our previous axiom. And in particular, we could have just replaced y by a finite set. And that wouldn't have changed anything. But yeah, it's sort of slightly more elegant maybe to put a y there. Okay, so that's the setting. And then what do we postulate? We postulate that this f will factor through a finite product of xi's. So we have this indexing set, it's discrete, but it can have an arbitrary size. And well, you can create a projection to a product of xi's indexed by any subset of I. And so we claim that this function f, or we don't claim, we postulate that it must factor through a finite product of xi's. In other words, functions from a product of compact Hausdorff spaces to a discrete set, those functions will only depend on finitely many coordinates. And that's again something, for example, if the xi's are finite, then you get a profinite set here. And for profinite sets, this is sort of a well-known phenomenon that if you're mapping to something discrete, then you factor through a finite stage. So again, it sort of extends that intuition. And then the final axiom, like we don't have any non-trivial supply of discrete spaces, so we postulate that the natural numbers are ODisc, and that will give us an infinite ODisc space, which otherwise we didn't have yet. Okay, so that's it. That's the long list of axioms that we postulate that constitutes our approach to condensed type theory. And so now I want to talk a bit about, well, what comes after that. So first of all, are we doing anything that makes any sense, or by postulating all this stuff, do we somehow end up with a theory that is inconsistent? So there is the following almost theorem, and it's an almost theorem because we're almost done with the proof. So if you consider the category of condensed sets, and I'm not really going to explain anything about what a condensed set is, but it's some version, some new approach to topology. This category is a topos, and every topos comes with an internal language. Classically, this internal language is a sort of first-order logic, but you can actually do a lot more than just first-order logic. You can just play all of dependent type theory. You can replay that inside a topos in a sort of internal reasoning. And so once you've done that, our axioms become claims that may or may not hold in any given topos. And so what we claim, basically what we proved, is that the topos of condensed sets satisfies all of these condensed axioms. And so whenever you would prove something in condensed type theory, that will automatically give you a theorem about condensed sets. And so this also provides a consistency check that our type theory has a model, and so it is not inconsistent. Well, unless ZFC is inconsistent, but let's not think about that. Yeah, so it's a relative consistency check. So we've been looking for other models, but unfortunately, even for example, if you take a scheme and then consider the pro-étale topology and then the pro-étale site, so you have the pro-étale site and then you look at the topos of pro-étale sheaves on a scheme, that's somehow spiritually very close to condensed sets, but it doesn't form a model, unfortunately. So at the moment, this is also the only model that we have. But so what we're hoping for, or what we're also looking for, is somehow a model that that has computable content, and so it should be of a much more finitary nature than condensed sets, because condensed sets are somehow involve huge amounts of data. But if we could have a very finitary, a model of finitary nature where everything is somehow computable, then this would actually give features like a computer algebra system to this type theory. And it's not completely unrealistic to hope for. So people have done several things in synthetic topology that are very close to that have a very computable flavor. So Yeah, but that's all I can say about this, because we don't actually have a model. Okay, so then I want to launch into this story about directed univalence. But let me maybe pause for a few seconds. Are there any questions so far about all these axioms, etc.?
Do you think light condensed sets? Does your proof work?
Right. So our proof is we take any cutoff cardinal kappa, and can work with that. So certainly light condensed sets are going to be a model, and one thing that shows is that it is consistent to add another axiom that every ODisc type is countable. You could add that and it wouldn't be a problem. Okay.
So
yeah,
maybe one more question. You mentioned synthetic topology. So have you compared this to this synthetic topology of Martin Escardo and I think Davorin Leshnik as a PhD thesis, where he shows something like that every complete metric space functions between complete metric spaces are always continuous. Have you looked at these settings?
Yeah, we've certainly looked at that, and there is a lot of spiritual overlap, but not really implications either way, or like models either way. So, for example, yeah, okay, I'll say a bit more about that later, maybe when I get to the real numbers. Yeah, but it was quite an inspiration, I think, or sort of guide. Yeah, a guide for us when we were trying to figure out what the right axioms were, and what the sort of initial sanity check should be when we started. Yeah, when we tried proving certain things inside this type theory. Yeah, so we started trying to prove things, and one of the things we stumbled upon is what we now call directed univalence. And so I'm sort of only going to sketch what the intuitive picture is in this talk, but the intuition of the claim is that if you consider the subtype of prop that consists of propositions that are ODisc, and yeah, so what does this mean? If you have a map from a type X to prop, then you can think of this as the indicator function of a subset of X. So if you have a map from X to O prop, then this would be the indicator function of a special kind of subset, and it will be like intuitively in the model, it will be an open subset. So O prop is the classifier for open subsets of X, whereas prop is just the classifier for arbitrary subsets of X. Okay. And so what we claim is that this behaves like a directed interval. So we'll see why. So we have two types, X and Y, both ODisc, and then we define a type of directed paths from X to Y. And this is just the type of all functions from O prop to ODisc, such that false is mapped to X and true is mapped to Y, because both false and true are open propositions, and they're also the only 2 points that you can actually find in an arbitrary context. And so then our theorem is that actually this type of functions from O prop to ODisc that satisfies these two conditions on the endpoints is naturally equivalent to the type of all functions from X to Y. And yeah, so, okay, that's somehow maybe a bit crazy. So why would that make sense? And we actually, okay, I should say that we have a formal proof of this in Lean. So we just take bare bones Lean and use the axiom keyword a bunch of times to state all our axioms, and then we prove a bunch of theorems and definitions using those axioms, and we have a formal proof of this natural equivalence. So what is going on? So I told you that OPROP is like the classifier for open subsets, and in topology, this role is played by the Sierpinski space. So the Sierpinski space is a two-point topological space. It has an open point and a closed point, and so maps to the Sierpinski space. If you take the inverse image of the open point, that should be an open subset. And you can also see that whenever you have an open subset, you just can create a map to the Sierpinski space that maps all the elements in the open subset to the open point and the rest to the closed point. And so the Sierpinski space is a classifier for open subsets. And right, so intuitively we think of OPROP as the Sierpinski space, and on the other hand, OPROP has this logical flavor of being about propositions. So we have this arrow from false to true, which is just the implication. False implies true. But this matches the generalization order on the Sierpinski space. So the closed point false generalizes to the generic point true. And now whenever we have a path, so this is one of those functions f from OPROP to ODisc that has x and y as the two endpoints, then in the model, you think of this as, okay, it's a map from OPROP to ODisc. So it means that in the context of an open proposition, you get some type, which is the image of that proposition under F. So it's sort of, you view OPROP as a base space, and for every point you get a type. So you have a fibration over OPROP. And so there's a picture that corresponds to that. So we have the Sierpinski space as a base space, and then we have a total space, and our path F is a fibration of this total space over the Sierpinski space. And the important point is that the map from OPROP landed in ODisc. So that meant that this fibration is like a local homeomorphism. And that means that if you have a point above the special, like if you have a point in the fiber above the special point, then that point extends to a section over a small open neighborhood of the closed point. So intuitively, because it's a local homeomorphism, whenever you have a point in the fiber above false, you can extend this to a section in a unique way, because it's a local homeomorphism. You can extend this to a section over the entire Sierpinski space, and in particular, you can intersect it with the generic fiber and find a point in Y. And so that is going to be how you get a function from X to Y. You take a point in X, you can map it to Y by extending the point to a section over the entire Sierpinski space. So that's the intuitive idea. And now we have to make this into a rigid proof, like a rigorous proof, using our axioms. And well, right, okay, this is what I just said. So what is the main proof ingredient? Well, in our axiomatic framework, we can define the space n infinity, which is the natural numbers together with a point at infinity. And the way you can define this is as monotone functions from the naturals to the Booleans. And then you have a finiteness predicate, which we call phi because finite, which is just, okay, if you have an element x of n infinity, that's a function from n to bool, we just ask, is there any element of the naturals that is mapped to true by this function x? And if that is the case, then you take the smallest such I, and then after that, everything will be mapped to true because of the monotonicity of x. And so the smallest such I, that is the natural number that is corresponding to this element x. On the other hand, if such an element I does not exist, that means that all I are mapped to false, and that is the point at infinity. So that's how n infinity works. But what we also see is, okay, so n is postulated to be ODisc, and bool is a finite type. It's a type with two elements. So that is going to be, by our most basic axioms, it's going to be both ODisc and CHaus. So we're taking functions from n to bool is like an infinite product of copies of bool. So that's going to be CHaus by our Tikhonov axiom. And then we're taking a subtype of that. And so now you have to look carefully at what the definition of monotone is. And it's going to be for all I, j, if I is less than j, then this implies that xi is less than or equal to xj. So for all, that means like it's a pi type. So this whole proposition, you just look at the structure, and it's a bunch of pi types of propositions that are actually decidable. And so decidable propositions are going to be both CHaus and ODisc. And so in the end, you find out that this is going to be a CHaus proposition being monotone. And so we're taking a CHaus subtype of something that was already CHaus. And that means that n infinity is a CHaus type. And this is all just sort of follows structurally from the axioms. And that matches our intuition, because n infinity is a profinite set informally. So it should in particular be compact Hausdorff. Okay. And now we have this finiteness predicate that maps to OPROP. Okay, so we can pull back our setting. If we have a path f, well, a path f from x to y, that is a map from OPROP to ODisc. And so we can compose it with this predicate phi, and then we get a function from n infinity to ODisc. And n infinity, as I just explained, is a CHaus type, whereas OPROP, we can't say anything about it. OPROP is neither CHaus nor ODisc. But because n infinity is CHaus, and we now have a family of ODisc types indexed by n infinity, now we can start using a bunch of axioms. And so then we need to use that phi somehow has a sufficiently dense image, and then we can make the whole proof work. So inside our axiomatic setup, we cannot prove that phi is surjective. It's somehow maybe counterintuitive, because OPROP looks like it has only 2 points, but you need to think about what happens in an arbitrary context where OPROP is sort of, if you think about it topologically, OPROP is a classifier for arbitrary open subsets. So in arbitrary context, there are many more open propositions available, not just false and true. And yeah, so we even, yeah, I claim that you cannot prove that it's surjective. It's just not a provable thing, and maybe even false. But it is sufficiently dense, whatever that means. And so we can use that to turn it into a proof, because now we have the point at infinity plays the role of the closed point, and then like open neighborhoods of infinity are just sort of intervals that start at some natural number and then run off to infinity. And yeah, you can show that things extend over some neighborhood of infinity. Okay, so that in that way we can make the preceding picture precise about extending points from the special fiber to a generic fiber. And so what is one of the crazy consequences of having these path types, and path types are equivalent to actual function types? Well, it means that whenever you have a function from ODisc to ODisc, so a function that sends arbitrary discrete types to other discrete types, then this extends uniquely to a functor. And how does that work? Well, you take two ODisc types and take a function between it. And now somehow, right, we claim that we have a functor and we know what it does on objects, and every mathematician who has never done anything with formalization will agree that it must be obvious what it does on functions. And now it actually is. There's only one thing that you can do. So whenever you have a function, by directed univalence, it corresponds to a directed path. And recall that paths are like functions from OPROP to ODisc that send, in this case, it must send false to X and true to Y. So that those are the endpoints of the path. And then if we post-compose this with F, right? So we take our little p and then we continue with capital F, then that will give us a path between the endpoints f of x and f of y. And then we use directed univalence in the other direction, and we end up with a function between those two endpoints. And that function must be what our functor capital F does to the function little f. And so this can actually be turned into a real proof, and you can show that it is compatible with identity maps and composition, and so you get an honest functor. Except that I told you a tiny little white lie. So such a function extends uniquely to a functor if it preserves canonical isomorphisms. And of course, nobody knows what canonical means, but in the proof, there are 2 points where you need to use that two types are isomorphic, and they're like barely not definitionally equal. If you look at it, if you don't know what definitional equality means, if you've never encountered it before, you won't understand why the two are not equal. They just look obviously equal, but they're not. So they're really canonically isomorphic, and you have to deal with this. And so really you need to do one of two things. Either you say, well, we add the classical univalence axiom from homotopy type theory to our setup, and then we know that whenever two types are isomorphic, then they're equal, and functions preserve equality, so their images will also be isomorphic. And right, so really what we're saying is, if you have a function that is sort of a functor of groupoids, that is functorial in isomorphisms, then you can extend it uniquely to a functor that is functorial in arbitrary morphisms. And so you can do one of two things. In our formalization, we didn't add the univalence axiom because that would be an insane amount of work in Lean. But we just added this functoriality in isomorphisms as a separate condition to the theorem. Okay, so that's what I wanted to say about directed univalence. Right, and so I told you, whenever you prove a theorem in condensed type theory, then somehow this should give you automatically give you a statement about condensed sets. And so what is this? Well, so we need to understand what ODisc means, right? Because we're talking about a theorem that is about functions from ODisc to itself. So what the heck is ODisc when you look in the model of condensed sets? Well, ODisc is a universe that classifies discrete spaces or local homeomorphisms or something like that. And so that means that in our base category for condensed sets, we have compact Hausdorff spaces, or maybe profinite sets. You can choose whatever you want. And so the local homeomorphisms mapping to a compact Hausdorff space that is equivalent to CHaus. This is by the espace étalé equivalence. So basically, if you have a family, like a local homeomorphism, which is a family of spaces living over K, that's what models an ODisc space. So if we want to know what all of ODisc is, that is going to be the category of sheaves on a compact Hausdorff space K, where K is now varying. K can plays the role of an arbitrary context. And so now this is going to be some sort of stack, the stack of, the étal stack, I would say. And so we denote by étal with this superscript isomorphism, the groupoid core. So for every K, we only remember isomorphisms inside this category of sheaves. Right, so that groupoid core is going to be a stack of groupoids over the category CHaus, whereas étal itself is a stack of categories over CHaus. And the claim that we prove with this internal theorem is that whenever you have a functor from the groupoid core to itself, then this extends uniquely to a functor of stacks from étal to itself. And that's somehow we showed this result to several people who are working in like pyknotic condensed mathematics, or somehow that part of maths, and they were somewhat surprised by this theorem, basically just as surprised as we were when we discovered the theorem in the internal language. Yeah, so what this suggests is that there are somehow certain special categories, and ODisc is one example, where if you have functions between those categories, then you only have to specify what they do on objects, and you get functoriality for free. And I think that is somehow pretty crazy. So let's see. I wanted to say a little bit more, and then I'm done. About real numbers, we can, of course, define the real numbers in type theory. And there are two canonical ways to do this. You can do the Cauchy reals, or you can do the Dedekind reals. And within our setup, they're not exactly the same, but we can add one more axiom, a so-called dependent choice, and then they will be the same. And actually, dependent choice is true in the model of condensed sets. So we could just add that, but this is basically the only place where we would need it. So yeah, we didn't include it in our list of standard axioms. Also because it's not so easy to give a direct topological motivation for it. And so we can show that the interval from 0 to 1, or like any finite closed interval, is compact Hausdorff. And so this gets back to the question that Benedict asked a moment ago. So we've been looking at this, whenever you have functions between the real numbers, or like subsets of the reals, or maybe products of reals, then you can just write down the epsilon delta definition of continuity. And the question is, within our setup, would every function be continuous? And I am not exactly sure if we ended up with a full proof of this. So we were thinking about this a while ago, and so we're not completely done yet, but it looks extremely likely that every function will be metric continuous. So yeah, that sort of matches with the ideas that are coming from synthetic topology. Okay, so future ideas. One would be to try to find a computable model of these axioms. We definitely want to explore further consequences of this idea of directed univalence. And if at all possible, we want to see if we can reorganize parts of the LTE proof using ideas from condensed type theory. So that's what I wanted to say. Thanks so much.
Thanks a lot for the talk. Do we have questions? I think there's at least one question in the audience here in Cambridge. Can you hear Angeliki talk? Okay, maybe
no.
You to come closer. Okay.
Johan, can you hear me now?
Yes, yes, I can.
The talk. I was wondering if you could elaborate a bit more on the computable model you were talking about. So in what sense would that be computable? Would you like to elaborate a bit more? So what is the information, the effective information you would be able to compute?
So somehow you would want the way you model a type should be done using a finite amount of information, or well, not exactly finite maybe, but maybe a finitely generated amount of information. And so concretely, if you think, for example, about the real numbers, then the real numbers are typically very non-computable. But if you start modeling them as a stream of digits together with a explicit rate of convergence to your real number, then you can do a lot more computations with it than if it's just random Cauchy sequences. You have no idea how to compute with them. Like you'll never know whether you're anywhere close to the answer or not. And so that sort of idea, you can try to push that to all types. And yeah, I mean, so far, I don't have any concrete ideas about where to look for an honest computable model. But what I've been told is that it's not unrealistic to hope for such a thing. So it's really on the future idea list, and so we don't have. Yeah, I'm not sure if I'm making much sense in elaborating on it.
Thank you.
Do we have further questions also from the online audience?
Yeah, I just wanted to ask a potentially simple question, but like, if you have this, okay, if you have a function which extends functorially to a functor between ODisc and ODisc, do we like, so what, do we have any relations between the different functors? Like, can we talk about natural transformations between these the functors we extend? Like, yeah.
Yeah, so right. So again, a natural transformation, you would only need to specify it on objects, and the squares that need to commute as a condition in the definition of natural transformation, you would get that for free. So you only need to say what it does on objects, and then you're done. Yeah, that will work.
All right. Yeah.
Yeah, so I have a question. In the model of condensed sets, this predicate ODisc, can you explain that a bit better? Is it not just being discrete in the usual sense?
I mean, it is being discrete in your usual sense, right? So so yeah, I mean, it's like you showed that there are 3 different ways, I think, or 3 or 4 different ways that you can classify discrete objects, and all of the that's exactly what we mean by ODisc.
Okay, I guess I just didn't really understand this where the étal stack comes in that you talked about.
Well, I mean, so what is a discrete object over a compact Hausdorff space K? That would just be an ordinary sheaf on K, viewed as a condensed set. Does that make sense? Because if you just start with a discrete topological space, that somehow lives over a point. But now, if you want to think of what do we mean by a discrete family of spaces over some space K? Well, then you need to take an ordinary sheaf on K, or like a local homeomorphism, or whatever, and they all end up being the same thing.
Okay.